participants group.
All right. Can you guys see my screen?
Yes.
All right, perfect. Okay. Thanks so much. Thanks for inviting me. Really excited to be here. So I'm Dorsa, and I'm very interested in studying human-robot interaction and actually thinking about it from an algorithmic perspective. And today, what I would like to do is I would like to talk about how we go about building computational models of humans, and specifically when the assumptions that we make about these models fail. So that's my plan for today's talk. So if you think about humans and robots interacting with each other, we usually think about a robot trying to model a human and the actions of the humans around it. Like in the assistive case, you'd imagine having a robot trying to predict how the humans around interact or how the human user is using the system. Or in the autonomous driving case, as you've already seen talks by Adrian and Marco, you think about pedestrians predicting how pedestrians act around you, or how even human-driven cars act around you. So in general, I don't think I'd need to motivate this much. If we have autonomous systems or robots interacting with people, it is actually important to go about building predictive models of how humans around us act and how they respond to our actions. And in a lot of our prior work, actually, we tried to do some version of it. So it kind of started with autonomous driving back in the day, where we started looking at actions of an autonomous car and how an autonomous car can influence people. Like, for example, how can it cut in front of people and make them slow down? But the interesting thing there was, well, there are human-driven cars around us, for example, this white car, and that white car might not be a timid driver that lets you in. So if you have an autonomous car algorithm that tries to do that, it needs to capture the fact that this human is not letting it in. So in this case, our car decided to nudge in and go back to its lane. So in this case, we were looking at driving style and predicting driving style in response to robot actions. Similarly, we have looked at the same sort of formalism for social navigation. This is work with Alison Okamura, and also worked with Silvio's group, Silvio Severis, Marinel Vasquez, where we are looking at predicting pedestrian motion around robots. And again, like we were looking at walking trajectories in response to robot motions, or in response to haptic feedback in the first case. And finally, we have looked at this in the setting of human-robot collaboration and coordination too, in the setting of assistive robotics, where you are teleoperating a robot and the robot needs to figure out what your goals and preferences are, like what marshmallow are you trying to pick up, or also in more like dyadic settings, where you're trying to, let's say, build a specific type of tower with this robot. And the robot, again, needs to figure out what humans' intents and goals are and what tower it's going for. So in like the common thing across these applications is we need to have some model of the human. We need to predict how the human acts or what the human's goals and intents are. So the way we think of this is we have a robot that's trying to do a task, interacting with a person, and the robot needs to build this representation, this predictive model of the person. And in most of our prior work, the way we looked at this was we either assumed that the person has some sort of reward function, some sort of objective in their mind. And then the way we went about it was that the robot needs to estimate that, needs to figure out what that reward function is. That estimate, let's say, is RH. And then the robot's model of the person is this policy that's a maximizer of this reward function. So the big assumption that we made in most of these works is humans are either fully optimizing a reward function, or maybe they're approximately optimizing a reward function. And that was kind of the framework that we've been going around with for a lot of these applications. And we did get like nice results. So it is like kind of working. But there are a lot of assumptions that we are making here. And today I want to just talk about 3 different assumptions that we are making and how can we go about relaxing those assumptions. So the first assumption is that we assume our humans are rational or optimal, or maybe at best case, they're noisily rational, right? So that's like how we go about modeling the human. The human is acting like rationally, optimally. And if you think about it, well, that is true in a lot of normal settings, but if you think about near accident driving scenarios or near the end of the risk spectrum in generally, it is not true that humans are acting optimally all the time. It turns out that they're actually more likely to act suboptimally when you're in near accident scenarios. So that assumption doesn't always hold. The second assumption is that when you think about the interaction, so when you think about this robot now interacting with a person, What we usually do is we usually try to get the robot build a model, a belief of how this person is acting, how this person is navigating, how this person is driving. And we have these belief models, and because of that, we got that driving behavior that the car decided to nudge in based on its belief of the other driver, what type of driver it is, what type of driving style they're using. And that is usually like that's like a very good formalism and a way of thinking about it. But the issue with that is humans themselves don't necessarily do that. Like when you look at a lot of interactive tasks, human-human interactive tasks, humans actually, like a lot of times, for depending on task, but a lot of times they tend to be very bounded rational. Like one thing we know about humans is that they're bounded rational. They're not going to be able to capture this high dimensional belief in their head. And instead, like they almost use heuristics a lot of times. They keep track of low dimensional things that is sufficient for them to achieve this task, like moving a couch with another agent. So given that, like that gives us actually a lot of hope that maybe we don't need to like fully model the opponent or the partner. Maybe there is something much lower dimensional that we can capture in order to better collaborate with the person. And then the final assumption that I want to briefly talk about towards the end of the talk is the fact that we assume humans don't change. Like we spend all this time doing, let's say, inverse reinforcement learning or imitation learning to learn these policies, to learn these reward functions. And then we usually like fix it or maybe change like one parameter. And the thing is, humans do actually change the moment you put a robot in their vicinity. Like the moment you put a robot in social navigation settings, like the model of human that you have is not going to work anymore, because now the human is responding very differently to the robot actions. And we need to think about this repeated interaction and how the model of the person changes over time. So, all right, so that's my plan for today. I'm going to spend most of the time on number 1 and a little bit of time on 2 and wrap up with the ideas in 3. Okay. All right, so going back to this picture, I think we all agree that this robot needs to model how these humans act around it. But if we go to slightly different scenarios where we have a person, let's say on a factory floor interacting with these large robots, or maybe we are in a near accident driving scenario, like we still need to be able to predict how these humans act in these safety critical settings. And the question is, do the models that we have built so far, do they just transfer, or is there a change when you're thinking about these near the end of their risk spectrum settings? So let me motivate that by an example. Imagine we have this red car. This is a red autonomous car that's trying to make an unprotected left turn. So it's approaching the intersection. It wants to make an unprotected left turn. And then we have this blue car that's coming down the road too. And at some point, the light turns yellow. And if the light turns yellow, then this red car should try to figure out if the blue car is going to stop or if it is not going to stop. If our autonomous car thinks that the blue car is going to be optimal, it would assume that the blue car will definitely stop because the light is going to turn red, like that is the optimal thing for the blue car to do. And because of that, it would decide to make a left turn. And that would be the optimal thing for the autonomous car to do based on this model. But I think we all have seen cars passing yellow lights or red lights. I've personally done that. So if that is the case, then these autonomous cars should try to be able to model the fact that humans don't always stop at yellow lights, and then we need to like consider these risk measures when we are planning for our autonomous vehicles. So robots must actually recognize that people can behave suboptimally when we are in risky scenarios. And so far, our models are more of the form of, well, I have a policy for my autonomous system, I have a prediction of my human agent here, human-driven car here. And that policy is based on optimizing some reward function that I've learned. So far, I've basically been assuming that I have an optimal action and humans, rational or optimal humans, are deterministically picking that action. I'm using rational and optimal interchangeably. I know they're different, but for this talk, let's say optimal and rational are the same thing. Okay, so that is kind of the thing that we've been doing in a lot of our prior work, and other people have also been doing in their prior work. And I think more recently, people have been realizing the fact that humans are not deterministic. Well, this is not a great model. So maybe we should try to capture the fact that humans are not deterministic. So one common model that's been used recently is this noisily rational model that assumes that probability of actions of humans is proportional to exponential of some theta parameter times a reward function. So this theta parameter is a temperature parameter. It's commonly called rationality coefficient. And if you put that equal to infinity, then you're getting your optimal action. If you're putting that equal to 0, then you're going to get random action. And depending on how you pick your theta, then you get this nice distribution that tells you that the actions of the human are probabilistic. They're coming from this distribution. The problem with the noisily rational model is that it still assumes that the most likely action of the human is the optimal action. And when we think about some of these risky scenarios, that's actually not the case. When we think about some of these risky scenarios, it turns out that there are scenarios where the most likely action of the human is a suboptimal action. So we would want to be able to have a model that actually captures the fact that maybe accelerating and running the yellow light is the most likely thing. And our model should be able to capture that. So the idea that we have been exploring is maybe we should have this risk-aware model that tries to capture this orange curve. And the way we go about that is actually by slightly changing the previous model. We still assume probability of actions of humans is proportional to exponential of theta times some reward. But the thing is, we are making non-linear transformations on this reward function based on ideas coming from prospect theory, and specifically the fact that we would want to model these risky behaviors on nonlinear transformations on the reward. Okay, so I'm not going to go into too much details of how we are doing it, but just briefly, the way that works is this reward function is a sum of product of these probabilities times reward of a specific event. And what we do is we make some nonlinear transformations on the reward. So instead of, if the true reward is a dotted line, our risk-aware model is the orange line. And this captures the fact that people think differently in terms of high reward versus low reward events. And there are a set of hyperparameters here that we tune based on data collected from humans. And similarly, if you think about the probability, we make some nonlinear transformations on the probability. So we overweigh low probability events and underweigh high probability events. This is actually the exact same phenomena that we see when people buy insurance or people buy like lottery tickets. Like people tend to overweigh low probability events. So the same phenomena, we bring in the same phenomena by changing the probability using this nonlinear transformation with a set of hyperparameters that could be tuned based on data from humans. And finally, we'll have this reward function that actually captures risk. So I want to show you just one quick example of how that works in practice on a simple robot experiment where we have a human and robot collaborating with each other on a task, on a block stacking task. So what they're doing here is they're moving these blocks sequentially and they're trying to build a tower. And they have two options. One option is to go for an efficient tower, but unstable. So picking the cups that are closer, but you end up with this unstable tower that's kind of like a Tower of Pisa. And if you build that, you're gonna get a lot of rewards. But the thing is, this tower only stays upright like 20% of the time. Okay, so you either take risk and go for this, or the other option is to build an inefficient but stable tower, making sure that the cups are put together in the decreasing order so they'll never fall, but then you're only awarded like 20 points. Okay? So if you consider these two options, actually the better thing to do in terms of reward is to take risk. The better thing to do is to go for building an efficient but unstable tower. And if you decide to have a robot collaborate with a person, and the robot assuming that the person is noisily rational, the robot would think that the human is going to take this risk, and because the human is going to be likely to be optimal, and because of that, it tries to go for the same cup that the human goes for, and then you get like this weird situation that the robot needs to replan and go and pick up some other cup. Here is actually seeing it in action. So Roberto is going for the orange cup. Robot is also going for the orange cup. It comes out empty-handed, and it needs to now replan and go and pick up something else. But if our robot models humans based on this risk-aware model, based on this idea of putting prospect theory into our human modeling, then what ends up happening is that the robot realizes that the human is overly concerned about the tower falling, and because of that, the human is going to take, or is more likely to take the suboptimal action and actually collaborates better with the human. So just to summarize some ideas here, what we're doing is you're capturing this suboptimal human behaviors using models that are motivated by cumulative prospect theory, and we're trying to use those in settings where we're near the end of the risk spectrum. And this was a work that we presented actually at HRI this year, mainly leading by Erdem and Minay. So that was kind of the first assumption that I want to talk about, right? Humans are not always rational or noisily rational. And the thing that I'd like to spend a little bit of time next is thinking about this interaction in a dyadic interaction setting where you have the human and robot trying to do a task together. And usually the way we think of that is motivated by how we think about human-human interaction. So if you think about human-human interaction, let's say two humans trying to play a game, like play a game of chess. The way we think about that is we say, well, this person is going to have a model of its partner or opponent, thinking about how the partner or opponent is going to respond. And then you could even like go further and say, well, this person is going to model the opponent thinking about the person. And that can go for a number of steps. And this is commonly referred to as theory of mind. And nth order theory of mind is when you think about n levels down this interaction. Right? This is also commonly referred as opponent modeling in multi-agent reinforcement learning. You can think about this as a Nash equilibrium that's emerging between the agents. But basically, you're trying to model everything, your belief of the partner. And this is a common approach that is used in the setting of human-robot interaction too, right? Like so far, everything I've said has been on the left side of the slide. You have the robot and the robot models the human, but you can also imagine the human has a model of the robot and the two kind of fall into this game theoretic approach where they need to plan based on the representations of their opponent. Okay? We actually did this in the driving setting. This was work with Anka, where we looked at an autonomous car interacting with a human-driven car. So we said, well, we have an autonomous car, so that autonomous car should optimize a reward function, but that depends on the actions of the human, and the human is going to basically respond to, and we use the model, inverse reinforcement learning model here for how the human drives. And we kind of like solved this two-player game. We made a set of approximations, but at the end of the day, we solved the two-player game where we thought about these interactions in a game theoretic fashion. And we ended up getting really like nice, interesting behaviors. Like we ended up getting the behavior of a car cutting in front of another car because it knows that the human-driven car will slow down. Let's say an autonomous car, white car in this case, for example, would cut in front of the person because it thinks about this game theoretic interaction. And that was really interesting. But if you go back to this interaction, this interactive task, I'd like to argue that this is not true for all interactive tasks. A lot of interactive tasks are actually not like playing chess. If you think about two people trying to collaborate with each other on building some sort of construction or building or something of that form, like Alex and Bob here, Alex is not going to be thinking, well, I wonder what Bob is thinking about my beliefs of the world and my beliefs of where I'm going to go next, right? They usually keep track of much lower dimensional things like cues that is enough for them to achieve the task. And I think like that is an interesting framework that we should start thinking about. Like when we think about human-human interaction, they usually have some sort of shared representation. I'm going to refer to that as convention. They have a convention, they build a convention. And then through repeated interaction, this convention actually changes. And that convention is usually just sufficient for achieving the task. You don't need to model everything about the other agent. That like blows up, like that's not very scalable. That blows up like very quickly. So thinking about the paradigm of human-robot interaction, I think we should think about conventions and how we can predict conventions as opposed to a full representation of a policy of the other agent. So the way I'm defining conventions here is that conventions are low-dimensional representations that can capture the interaction and can actually change over time. And given that, I think there are a lot of interesting questions that comes up when we think about interacting with a human. So what are conventions? Can robots directly learn conventions from interactions? And we are thinking about these questions in a variety of human-robot interaction settings, but I just want to briefly mention one of them, where we have a human teleoperating a robot, using a joystick and teleoperating a robot. And you might say, well, why do you need a convention here? The human is just operating the robot. What is it predict? What is the robot predicting? Well, the thing is, the human is using a joystick with lower dimensional inputs, like maybe 2 degrees of freedom, but the robot has 7 degrees of freedom. So the robot needs to make sense out of human's input and build this convention between the human and robot and figure out what this input means and predict what the human really wants to do. So we've been looking at that in the setting of assistive teleoperation because it is actually really difficult to teleoperate robots. So here you can see a user trying to teleoperate the robot using this Jayco arm. The thing I want you guys to look at is his hand here. He keeps pushing the side. And the reason he does that is he tries to change mode between the linear mode and angular mode so he can control all the 6 degrees of freedom. And that takes a lot of time and energy. So our idea is, sure, assistive robots are dexterous. This dexterity makes them really hard to control, But what can we do? Can we have a more intuitive way of controlling these robots? And we think the answer is yes. We think depending on conditioning on the state, you can actually learn a much lower dimensional representation, a convention that makes controlling this robot much more intuitive. For example, if you know a robot is moving on a sine wave, you don't need all those degrees of freedom to control it. You can have a 1 degree freedom getting the robot move on a sine wave, like +1 and -1, we'll just do it. So given that, what we do is we collect a set of data, expert demonstrations of high dimensional motion, and then from that, we try to learn these low dimensional conventions that makes it easier for the robot to predict what the person really wants in this particular case. So this is actually an ICRA work, so I'm not gonna go too much into the details of it, but the approach we use is we're using conditional variational autoencoders to learn these latent representations of actions, Z's, and then we can replace here our encoder by just like a person that uses this latent action to control the robot. Just quickly showing how this works in practice, we are comparing end effector control versus using conventions. On the left is end effector control, on the right is latent actions. So this is kind of a long horizon task making an apple pie. And you can kind of already see that the person is having such a difficulty using end effector control on switching between the modes. But on the right, it's much more smoother, it's much more easier to actually get the robot to move around. And this person doesn't have like any experience with this robot, but like it's easy, the convention is easily introduced between the human and robot. And with 2 degrees of freedom, you're able to like achieve a task that kind of looks like this, much faster, much easier. We've actually added shared autonomy on top of this. That's a work that we're presenting at RSS this year, but I'm not going to talk about that. So just to summarize really quickly, what we were doing here is we're embedding these personalized behaviors into latent spaces, conventions that could actually be used for better teleoperating the robot. And Dylan will be talking about this at ICRA this week. All right, so I know I don't have that much time, so I just want to quickly summarize with this last assumption that we tend to make. We tend to make this assumption that humans don't change. Okay? But in assistive teleoperation, we see humans change all the time. Like the moment that you start using the robot, it's very different from a few hours later. We see this in settings where people use exoskeletons, and that's actually like a much more challenging problem because humans get used to these systems, and over assistance is a big problem. So if humans get used to the system, and the system, the whole point of it is to help the person walk again, like that is not so great. So the robot needs to be able to predict the fact that humans change, and it needs to change in response to that. We see this in driving. This is actually a picture of San Francisco. I used to live in SF, and there are these cruise cars in SF that tend to get stuck. And then when you bike, like when you see them now, like when I see them and bike around them, I just go around them because I know they're probably stuck at the intersection. And that's kind of interesting because we have an autonomous car that's not even there yet, but like I have actually like adapted to this autonomous car, and my behavior has actually changed based on only a few interactions that I've had with this autonomous car. So I think it is important to think about adaptations a little bit more carefully. Just very briefly, one way we've been approaching this is a work where you've looked at a hierarchical way of learning the changes in the dynamics of the reward function. So if I have an autonomous car and a human-driven car, and my autonomous car decides that this human-driven car is letting me in, I'm going to cut in front of it. You assume, you build a model of the human, this orange car, and you assume that this human-driven car is timid or is allowing you in. But the thing is, the moment you cut in front of it, that car is going to get really angry. And maybe it'll come back around and cut in front of you. So that model is not valid anymore. Your actions actually change the reward function of this human. And one way to go about it is we are taking this active learning approach where we're thinking about a hierarchy of asking queries and realizing how this reward function changes, in addition to just simply learning the reward function, how these mode changes emerging. And this is my last slide. So finally, everything I've said, both in the setting of assistive and in the assistive robotics and the setting of driving, it's all about like short-term, a few interactions, a few repeated interactions. But I think a lot of these questions become very interesting when you think about long-term interactions. So what happens when you put in a bunch of cars interacting with each other over years of driving? So what are the behaviors that emerge? So here on the left, you see a picture of Tehran, which is where I grew up, and that's driving there, and a picture of Palo Alto and driving in Palo Alto. They're very different. They both work kind of okay. My Persian friends always laugh when I say they work kind of okay. But they work. They're two different driving cultures. And the reason that they emerge is because we have had this repeated interaction between the agents, different equilibria, different conventions emerge through long-term repeated interactions. And one thing that we're looking at in general is a fleet of vehicles. And when you put in autonomous cars on the road, like a number of autonomous cars on the road, how can the actions of those autonomous cars influence routing decisions or influence conventions and equilibria that can emerge when you have autonomous and human-driven cars driving right next to each other. So with that, I would like to thank the group and thank you guys.
Great. Thanks, Dorsa, for the nice talk. I think it pushed us to a little bit to rethink about how we should really model human-robot interactions. For the sake of time, I just read you some of the questions which you can find already in the chat, and maybe you can afterwards also offline answer them. Maybe we can pick the one by Anka. So isn't accelerating and running the yellow light optimal under a different reward function? In general, what are your thoughts on this ambiguity between a different reward explaining the behavior versus a particular bias explaining the same behavior?
Yeah, that's a very good question. Yeah, so it depends. That's very true. So you can kind of think about this as a reward design problem or as like a prospect theory problem. Whatever reward function you decide on, let's say that you decide on something else as the reward function, then if you end up in some other scenario, risky scenario, that reward function might actually not hold, right? So this transformation actually matters when we are near the end of the risk spectrum. You could also imagine that there are maybe two very different reward functions that are happening and that's actually what prospect theory does, right? Very different transformations of the reward functions happening near the end of the risk spectrum or normal scenarios. But sure, you can change your reward function, but then similar transformations would need to happen in slightly different scenarios.
Mm-hmm. Thanks. Maybe also the question by Jeff Shamma, what about suboptimal behavior but uncertainty perception of the other party? For instance, did the car notice the yellow light or also higher order beliefs? Does the other car know that I know that he saw the yellow light?
Yeah, that's also a very good point. And I think it relates a little bit back to what Adrian was talking about. And a collaboration that we have started actually with TRI, trying to think about like these causal relationships between different agents. And do we need to do all these like multiple levels of beliefs, or is there some sort of relational graph structure that we need to keep track of and we need to change over time? Because like multiple higher levels of belief modeling would also not be very scalable. But these things do matter. Like we are simplifying the problem like quite a bit here. Like we are assuming that you don't have any uncertainty in the perception in the case that I've been talking about. But I do agree those actually make a huge difference and they need to be modeled. The question is, how do we model it? Like, do we model it based on beliefs? Do we model it based on some sort of dynamic graph that's changing over time? Yeah.
Okay. Thanks. Maybe, as I said, you can answer the other questions on the chat and we go on with the program. Thank you again.
Okay, thank you.